Alright, so as our notes packet says, let's get some basics down on acids and bases. So these are our definitions of an acid and a base. An acid is a compound that's going to produce hydronium ions when dissolved in water. And a base is going to produce hydroxide ions when dissolved in water. Now you should hopefully remember these lovely terms because they are polyatomic ions, hydronium and hydroxide. We memorized those back in the day. But exactly what are they? Well, a hydronium ion is essentially when a water molecule gains a hydrogen. And so now instead of being H2O, it's H3O with a +1 charge. There are several places and different books and areas where they might represent hydronium as an H+, but I like to really focus on trying to use hydronium every time I mean hydronium. And you'll see that as we go here. Hydroxide, on the other hand, is when a water molecule loses a hydrogen. And so if that happens, then it goes from being H2O down to OH with a -1 charge. And so that's what those two ions are. This next part is pretty important. The self-ionization of water. It is the driving force of acids and bases. Essentially, in any given sample of water, two water molecules can bump into each other, and when that happens with enough energy, one of the water molecules will take a hydrogen away from the other. So you end up with hydronium and hydroxide. At the same time, hydroniums and hydroxide can bump into each other and go back to being water. And so that's why we see this little reversible symbol in the middle of that reaction. Now let's take a look at this with a little visual skit. So as you see here, most of the time water exists as water, 2 hydrogens per oxygen, H2O. Well, sometimes they'll bump into each other and one of the water molecules will become hydronium, the other will become hydroxide. And again, at the same time, they can bump into each other and go back to being water. Well, in every water sample, as it says there, this happens at a very slight amount. Only 2 in every 555 million water molecules are involved at any moment. But it does happen. Now, I'll save that for a moment. So now what we have is, in a neutral solution, we'll have the same amount of hydronium and hydroxide. And that's like what we have in pure water. At any given moment, there's going to be some hydroniums and hydroxides, but you can't have one without the other, because every time a hydronium is made, a hydroxide is made as well. So what this definition for neutral solution says is the concentration of hydronium equals the concentration of hydroxide. And that's what I have here. The brackets around those ions or around any substance represents concentration. And most likely we use molarity, which we just got done studying. So again, in a neutral solution like pure water, the hydronium ion and hydroxide ion concentration is equal. So what we end up having, again, as the foundation of our acid and base studying, is this ion product constant for water, which we symbolize as Kw. If you take the concentration of hydronium times the concentration of hydroxide, you will get this magical constant, which is 10 to the -14, and that's a capital M squared, molarity squared. Concentration times concentration. And this is important. Again, all acids and bases are dissolved in water, and so this is always going on because they're always going to be an aqueous solution. And so essentially when you break that apart, again, in a neutral solution, the concentrations are equal. So when you multiply them together, if they get 10 to the -14, that means each concentration is 10 to the -7. So the concentration of hydronium is 10 to the -7. The concentration of hydroxide is 10 to the -7. Molarity. Molar. So when we put them together, 10 to the -7 times 10 to the -7, That's how we get the 10 to the negative 14. And so this again happens in every neutral solution like water. It's the ion product constant for water. So now what if something goes into this water, like hydrochloric acid? Hydrochloric acid goes into the water, and what ends up happening is it ionizes. It loses that hydrogen. So now we have a chloride ion, a water molecule, and a hydronium ion. We don't have the balance anymore because something was put in the water. It wasn't water by itself. So now, as it says there, there's insufficient hydroxide to balance the hydronium. And so we end up having more hydronium, and that is an acid. And as you see down here, the higher the concentration of hydrogen ions, hydronium ions, the stronger the acid. Alright, so again, regular water, normal concentration is 1 times 10 to the negative 7 molar. If it goes up, then we're going to be talking about an acid. So what we have for our definition of an acidic solution is, again, reading those brackets, the concentration of hydronium ions is greater than the concentration of hydroxide ions. As we've already kind of started talking about, acids and bases are opposites. So when there's more hydronium, that's an acidic solution. If there's more hydroxide, that will be a basic solution. And how I have it written here, the concentration of hydronium is less than hydroxide. Or you could write the concentration of hydroxide is greater than hydronium. Either way. In science class and in chemistry, basic solutions are also called alkaline solutions. So if you've seen that word around, that is what we're referring to. You might have seen an alkalinity test at a pool or with a fish tank or something, or alkaline when referring with batteries, but that's where that name comes from. So just a small little review. Again, pure water by itself, waters can bump into each other and create a hydronium and hydroxide. So pure water, we have a neutral solution, and that's where the concentration of hydronium is equal to hydroxide. Well, if we put in an acid, then we disturb that balance. Okay, and so that's where we end up having an acidic solution. Concentration of hydronium is greater than hydroxide. If we disturb with a base, then we'll have more hydroxides than hydronium. And we don't really like to work with these concentration numbers, 10 to the negative stuff. They're not very user-friendly. So that's where we end up having the pH scale. And so our last definition is here. If we want to find the pH of a solution, we're going to have to use the logarithm function. And the pH is the negative log of the concentration of hydronium ions. The pOH is the negative log of the concentration of hydroxide ions. Together, the pH plus pOH will always equal 14. We're going to be working with this information and with these calculations over the next several days, but I just wanted you to get the definitions down. Alright, finishing up here, we're just going to refresh our memories with some common acid and base formulas and names. HCl, hopefully you remember, hydrochloric acid, that's the lovely acid that's in our stomach. Sulfuric acid we've used several times this year, H2SO4, as Bart tells us, not a toy. And remember, SO4 is sulfate, so H2SO4 is sulfuric acid. NO3 is nitrate, so this HNO3 is nitric acid. If you remember, back in the day, we put nitric acid on a penny in one of our labs and it cleaned it up because it was reacting with the copper surface. PO4 is phosphate, CO3 is carbonate, so we have got phosphoric and carbonic acid. Very, very prevalent in our carbonated beverages, our soda pops. Check out the ingredient lists if you don't believe me. CH3CoO, that is acetic acid because CH3COO is acetate. Acetic acid is the main component of vinegar on your fresh cut fries, but CH3COOH is vinegar, or acetic acid. So those are some of the names and formulas for our common acids. Switching to the base side, sodium hydroxide, of course, OH is hydroxide, and we've used this again in lab, but the common name for this is lye, and it's very prevalent in drain cleaner, as you see here, Drano. That's where that name lye usually is associated with. Calcium hydroxide, again, you can see the hydroxide in the formula. If you ever see the white stuff seeping out of the mortar between bricks, that is calcium hydroxide. Potassium hydroxide, very common in liquid soap, soft soaps. As you remember, bases are much more prevalent in the cleaning and detergents and all that kind of stuff. Aluminum hydroxide is one of our several bases that can be used for antacids. That's where that name comes from, antacids. They counteract the acid in your stomach. But aluminum hydroxide is found in this classic milk of Mylanta. Mylanta, that's a antacid brand. Whereas magnesium hydroxide in milk of magnesia. There was a commercial back in the day, milk of magnesia mom. No one takes care of you like mom when you had an upset tummy. But that's the active antacid in that type of, the active base in that type of antacid. And lastly, we have NH3, which is ammonia. It is a base. It looks a little different because it doesn't have hydroxide in it, but we'll be getting into that. And obviously ammonia is used for cleaning, and we smelled it in that one lab, and people said, oh, it smelled like hair dye. And I mentioned that, indeed, it's used in smelling salts. So here's a picture of someone getting knocked out, and then if you haven't seen these cute little guys, hold on, you can look it up on YouTube. But these are the fainting goats, where they're little small kind of pygmy-esque goats, and when you chase them around, then they end up fainting. I'll let you see. They just drop over like they fainted. And again, you can search that on YouTube and offer them some smelling salts with the ammonia in it. Alright, so that concludes your homework portion of the notes, and we'll be getting into many other fascinating avenues of acids and bases over the next several days. Enjoy.